Alright, so today we're going to be working on the experiment on calorimetry. So we're going to be looking at a heater reaction. And to do that, we're going to use a special ice calorimeter that we have here. So the way an ice calorimeter works is, right in the center, on the central test tube right here, we're going to do a chemical reaction. Now the chemical reaction is going to be exothermic, so it's going to give off heat. Now when the reaction gives off heat, just on the outside of that central test tube, we're going to fill this with ice. And as much ice as we possibly can. When the heat's given off from that central test tube in the reaction, it's going to go into melting ice. Now the density of water and ice are not the same. So when we start melting some of the ice and it goes to water, volume is going to start to decrease because ice is less dense than water. So as it melts, it's going to start to contract. So we're going to see a volume change going on. So it's through that volume change that we can figure out, and this is developed in your lab manual, how much heat was given off based on how much ice melted, which caused a specific volume change to occur. The key to this experiment is to pack the ice calorimeter very effectively. So you're going to have to get yourself a little bit messy here. You're going to shove a whole bunch of ice into the ice calorimeter. Now you really want to pack as much ice into the calorimeter. You're going to get ice all over the place, that's fine, it's just water, it happens all the time. You want to pack as much as you possibly can. Hands are going to get cold. That's alright, you're tough. The key is pack as much as you possibly can. So I filled the ice calorimeter with about as much ice as I possibly can. I'm going to come over to the sink now. I just want to fill it with water. So I'm going to come to the distilled water tap and fill the water up to the top. If at this point you notice that a lot of your ice melted down, you may want to pour some of the water out and try to jam some more ice in there. The more ice you have inside the calorimeter, the better. Okay. So what we're going to do now is we're going to put our pipette onto the calorimeter. So you want to put it down as far as you possibly can. We've got our septa here. I'm just going to pull it off. The pipette should have the pointy end up. I'm going to make sure there's the most area to read. I'm going to put it in. What happens is the septa just seals on top of this opening. Seal. Make sure it's nice and straight. Next step is we're going to take our syringe with the little rubber hose, take the plunger off, put the rubber hose onto this section, and we're going to fill this up now with a little bit of water. What this is going to do is it's going to fill our calorimeter completely with water. So I'm going to put the plunger in. And what you should notice is as I depress the plunger, it's going to push water into the calorimeter, and it's going to cause the water level in the pipette to go all the way to the top. What we want to do is, we want to get that water level as high as we possibly can. Now, there's naturally heat coming in from the surroundings to the calorimeter. So that volume is going to be going down and going down as we are heating up this calorimeter. So we want to cool it down as much as we possibly can. So what we're going to do is we're going to take our big beaker here, put a little ice on the bottom, and we're going to start filling this beaker with as much ice as we possibly can. The key to this is you want to have all of the calorimeter completely isolated from the surroundings. So we want as much ice around it as we possibly can. This is going to prevent ambient heat from transferring into the calorimeter and making our results inaccurate because we're looking at the transfer of heat. So we don't want excess heat coming into our reaction. So put a lot of ice on top of the calorimeter, make sure it's well insulated. What we can do is, we're going to take a few minutes right now, and we're going to let the calorimeter stabilize. What you're going to notice is, at this point, the volume is going down a little bit. The whole system isn't cooled down to 2-3 degrees Celsius yet. Still a lot of heat transferring around. So we're going to let that happen. We're going to give it maybe 3 to 4 minutes to happen. During that time, what I've done is, one, we're going to put one of our reagents inside of the calorimeter. So depending which reaction you're doing, you're either going to do the oxidation of magnesium or you're going to do an acid-based, you know what I'm talking about, an acid-based neutralization. So either one of those, you want to put one of your reagents inside of the calorimeter. The other reagent, you want to get nice and cooling inside of an ice bath. Okay? You want everything to be cold, obviously, before you start the reaction, because if these are at ambient temperature, at room temperature, and you pour them in, they're going to have to cool down, and that's going to be an artificial source of heat into the reaction. So what we're looking at now is, if our calorimeter has been created nicely and created well, we can look at this volume of water in the pipette, and it should be nice and stable. So I can push it back up to the top, and we're going to see, is it coming down or not? You want to wait until that's nice and stable. Mine's still going down a little bit. It may take another minute or two for it to stabilize, meaning that the ambient heat's not coming into the calorimeter. Okay? Once this level's stable, we can start our reaction. Okay? But the first thing we're going to do before we start our reaction is we're going to take a couple initial points. So we haven't started the reaction. We're going to start taking measurements at every 1 minute intervals. Okay? So we're going to look at our volume here and say, at 1 minute, what's the reading? At 2 minutes, what's the reading? 3 minutes, what's the reading? What that is doing is it's giving us a baseline about how much ambient heat is coming into the reaction. We may not be able to stop this volume from going down. We want to minimize it, so we're going to let everything stabilize. But in the event that we can't completely stop it, we want to get a baseline and just understand naturally how much is coming in, so we can subtract that out in the end. So it looks like my volume is fairly stable. I'm going to take those first 5 minute readings. After those 5 minute readings are taken, I'm going to take my reagent. I've got another reagent in here. That's going to start the reaction. Now it's at this point the reaction is going to take place. Lots of heat is going to be released into the calorimeter, and your volume is going to start dropping very, very quickly. So you're going to take readings every 15 seconds at that point. What you're going to do is you're going to take those readings until you see the volume not changing very much. When the volume's not changing very much anymore, that means the reaction's done. And when the reaction's done, you're going to take another 5 baseline readings at 1 minute intervals. So you're going to end up with a graph that looks approximately like this if we were to plot volume versus time. We're going to start off with our first 5 readings up here at 1 minute intervals. They should be fairly flat because not much heat should be coming in. And then we're going to start our reaction and take readings at every 15 seconds. During this time, we're going to see the volume decrease substantially. Because now we've done the reaction, heat's being released in. We get down to the end, we're going to notice that our reaction is going to slow down, and we're not going to see much change in the volume. So it's going to start to flatten out. When it flattens out, we want to take another 5 readings at 1 minute intervals to get our secondary baseline. What this baseline tells us is naturally how much heat is coming in without the reaction. So we can draw 2 lines for our baseline. That'll show us what's naturally happening. And the change between those 2 lines is the volume change associated with the reaction. So once we have our volume change for the reaction, we can relate that back to how much ice was melted. We know how much energy it takes to melt that much ice. All that energy must have come from the reaction. So you can calculate a heat of reaction, and you want to base it on a per mole basis for one of your reagents, and you can report that. You'll finish this experiment up in the lab. Again, you want to do your calculations, calculate your heat of reaction, write up a brief discussion, mostly centered around your sources of error, and hand it in to your TA before leaving.